In this chapter, we're going to look at experimental error, how to deal with it, and how to calculate how the error propagates. We're going to start by reviewing the idea behind significant figures. And so in general chemistry, we said significant figures were the number of known digits in a measurement plus the one that is uncertain. Our textbook actually defines significant figures in a slightly different way, which is quite clever actually. And it is defined as the minimum number of digits to write a number in scientific notation, and here's the clever bit, without loss of accuracy. And the reason this is clever is as follows. So if we have a number like 138.0, then we can write this in scientific notation as 1.380 times 10 to the 2. And so we can see that there are 4 digits here representing the 4 significant figures. And so any more or any less digits would not be correct. We can take a very small number, such as 0.000000102, and we can translate that to scientific notation as 1.02 times 10 to the minus 7, in which case we have 3 significant figures here. Now, there are some rules when counting significant figures. If I go to a new slide, I can go over them. We can go ahead and we can review the rules of significant figures. So basically, any non-zero digit counts. Any captive zero counts. So, for example, a number like 382 ampere would have 3 significant figures, whereas a number like 302 kilograms would also have 3 significant figures because that zero is held captive between 2 non-zero digits, and so that makes it significant according to our rules. The last thing we have to worry about are zeros. Actually, there's 2 other things we have to worry about. Leading zeros are never significant. Those are zeros before a number, so 0.037081 candela. Why not? The 3, the 7, the 8, the 1, they all count. The captive zero counts. And the leading zeros are the numbers to the left-hand side before you get to the first significant figure. So they don't count. That leaves us with 5 significant figures here. And then the last place you can have zeros at the end, and that is called a trailing zero. And trailing zeros may or may not count. They count if there's a decimal point. They do not count if there is no decimal point. So an example would be something like 300 or 3080 versus 30.80. So in this case here, we know the 3 and the 8s count. The captive zeros count for both of them. But the 0 to the right-hand side, there is a lack of a decimal point in the first one. There is a decimal point in the second one. And so that means that the first one only has 3, whereas the last one has 4 significant figures. Hopefully these rules are familiar to you from introductory chemistry. In general, the last significant figure contains the error, and the last significant figure here, the last digit that's significant, is treated as having an error of plus or minus 1. The idea in this section is that every measurement you make has some error unless you are counting, and we are just assuming that the error is always plus or minus 1 in the last digit of every single measurement. Once we are required to add or subtract measurements that have been made, we have to follow the rules that the fewest number of decimal places limits our final result. So, for example, if we have 2 numbers, or 2 measurements, like 320 grams and 18 grams, okay, then we can add them together by actually converting both of these to scientific notation. So we would write 320 as 3.2 times 10 to the 2 grams. Notice that this digit here is not significant. That trailing zero is not significant without a decimal place. 18 grams Well, we could write it as 1.8 times 10 to the 1, but in order to add it together, we have to have the times 10 to the power is exactly the same. So we could write it as 0.18 times 10 to the 2. Okay, notice we have the correct number of significant figures. And we bring these together and we get 3.38 times 10 to the 2 grams. If you notice here, this digit here has 1 digit after the decimal point. This one has 2. And so this one is the weakest link. It tells us that our final answer should really only be quoted to 1 digit after the decimal place. So really we couldn't go past that underlying digit there. Our book uses the notation of sort of drawing a very small number down below, a subscripted number, to show that the number is not actually significant. We could round that and write that as 3.4 times 10 to the 2 gram if you prefer, or we could write it as 340 grams. Now if we look at another subtraction, we'll see that there's a trap, so we can learn how to spot the trap. Maybe we've got two masses and we want to subtract one from the other, so 1.3829 grams minus 0.1719 grams. The trap is our calculator. Those last two nines there will cancel out. Our calculator won't even display a number here, so it'll say 1.211. Of course, we know the units are grams. Why do we have to worry about this? Well, this has 4 digits after the decimal. So does this one. So our final answer should also have 4 digits after the decimal. And of course, our calculators will remove all the zeros at the end of a number if they're just infinite numbers of zeros in a row. But we still have to write it in. So we'd have to write 1.2110 grams in order to write it to the correct precision here. Now, in terms of rounding, we haven't really discussed rounding too much before. And we oftentimes in general chemistry just removed the first digit that was insignificant, and if it was a 0, 1, 2, 3, or 4, we basically just removed it and went on with our life. If it was a 6, 7, 8, or 9, we basically removed it and rounded up. And in introductory work, we normally took the 5 and we went ahead and we removed it and rounded up as well. But Harris is actually going to approach the case of a number 5 slightly differently, and let me go to a new slide and show you what I mean. First off, why do we need to worry about this stuff? Well, imagine we've got the 10 possible digits at the end of the number that we need to remove, going all the way from 0, if I can count, to 9. If we remove a 0 from the end of the number, then we have basically not altered the number at all. If we remove a 1, a 2, a 3, or a 4, then essentially 4 times out of 10, we have rounded down. We have decreased the size of the number. If we look at a 6, a 7, or 8, or a 9, and we round up, then we can see that 4 times we have increased the size of the number by rounding up. And the question is what to do with the number 5. So in elementary work, we just say, well, let's just round it up. The danger with this is that 5 times out of 10 we round up, we increase the number. 4 times out of 10 we round down, we decrease the number. And 1 time in 10 there's no change to the number. So there are 5 ups, 4 downs, and 1 no change. So there's an ever such slight bias to, in dealing with thousands of numbers, to slightly enlarge the number by doing it this way. And so more advanced methods actually, in the case of a 5, say we need some mechanism to ensure that half the time we round it up and half the time we round it down. You could do this a lot of different ways. So one way is to flip a coin. Every time you have a 5, you can flip a coin, and if it's heads, you round up, and if it's tails, you round down. Or you could imagine any number of different mechanisms that give you a 50-50 chance. Harris uses the even digit rule, so he rounds up to the next nearest even digit. And this essentially, assuming the numbers are evenly distributed, gives you a 50-50 round up. What do I mean by that? If you've got a number like 3.85, then, well, 8 is already even, so it can just round to 8. But if you've got a number like 3.55, then 5 here is odd, so we round up to the next even digit. That would make it 3.6. So you can see essentially half the time, depending on this digit here, if it's already even, you leave it alone, so you're rounding down. However, if it's odd here, so a 1, a 3, a 5, a 7, or a 9, you're going to round up to a 2, 4, 6, 8, or essentially a 10. So half the time you're going down, half the time you're going up, so that bias of, on average, rounding up more times than you're rounding down is going to be eliminated here.